Good day, everyone. I am your presenter for today, Frank Christian V. Dichoso from CE1A, and today we're going to talk about graphs and circuits. For our learning objectives, at the end of this lesson, students should be able to understand the historical background of graph theory, familiarize the definitions of properties of graphs, differentiate what is loop, path, degree, and circuits, enumerate and differentiate types of graphs, define equivalent graphs, and understand the concept of circuits. For our topic discussion, we will start at the historical background of graph theory, followed by the definition of properties of graphs, followed by the definition of loop, path, degree, and circuits. Next will be the types of graphs and its differences. The fifth will be the equivalent graphs, and last is circuits. And now let us start our topic. For our introduction, according to Collins Dictionary, a graph is a mathematical diagram which shows the relationship between two or more sets of numbers or measurements. Graphs are a common method to visually illustrate relationships in the data. These are most commonly used in mathematics, generating graphs in studies for complication of works. Moreover, there are many types of graphs. Later on, we will discuss each of it and give examples. On the other hand, according to Merriam-Webster, a circuit is a path that starts and ends at the same vertex. The historical background of graph theory. Graph theory is a study of lines and points. It is a subfield of mathematics that deals with graphs. Those diagrams composed of points and lines and often illustrated and represents mathematical truths. Graph theory is the study of relationship between edges and vertices. Came from the lines and points. The history of graph theory may be specifically traced to 1735, when the Swiss mathematician Leonhard Euler solved the Königsberg Bridge problem. The Königsberg Bridge problem was an old puzzle about the possibility of finding a path over every one of 7 bridges that span a forked river flowing past an island. But without crossing any bridge twice, Euler urged that no such path exists. His proof involved only references to the physical arrangement of the bridges, but essentially he proved his first theorem. The question posed to Euler was straightforward. It was possible to take a walk through the town in such a way as to cross over every bridge once. Euler, recognizing that the relevant constraints were the 4 bodies of land and the 7 bridges, drew out the first known visual representation of the modern graph. A modern graph, as seen as in the image below, is represented by a set of points known as vertices or nodes or points that is connected by a set of connecting lines known as the edges. The vertices represents the lead masses and edges represents the bridges. Euler observed that when a vertex is visited during the process of tracing a graph, it must follow that there must be one edge that enters in the vertex, there must be another edge that leaves the vertex, and therefore, order of the vertex must be an even number. That's why Euler found that only those networks are transversable that have either no odd vertices, then any vertex may be the beginning and the same vertex will also be the ending point. And exactly 2 odd vertices And one odd vertex will be the starting point and the odd vertex will be the ending point. And now let's move on to the definition and properties of graphs. In mathematics, graph is a diagram showing the relationship or the relation between variable quantities, typically of two variables or more. Graphs are usually formed from various data points, which represents the relationship between two or more things. Each point, stroke, color, or shape of an graph has a different meaning that helps in interpreting a graph. And when we talk about graph, most of us have an idea of what it looks like, just like the figure shown below. A Cartesian plane with a function graph on it, yes, it's a graph, just like bar graphs, pie charts or pie graphs, and many more. This might be the idea when we say graphs, but we will be not dealing with this as we tackle this lesson. Graphs come with various properties which are used for characterization of graphs depending on their structures. These properties are defined in specific terms pertaining to the domain of the graph theory. In this chapter, we will discuss a few basic properties in all graphs. Let's talk about graph. A graph is a collection of vertices connected to each other through a set of edges. Just like what I've said earlier, and graphs has two main parts, and these are the vertices and edges. Vertices are the dots or vertex if it's just one, and edges the one who is connecting two vertices or more. And now let's differentiate loop, path, degree, and circuits. Loop is an edge that connects a vertex to itself. Path is a sequence of vertices connected by edges. Next is degree and circuit. Degree of a vertex is the number of edges incident with that vertex. Circuit is a path that begins and ends at the same vertex. Take a look at the given figure below. We have a graph here. Let's say we are here at vertex 1. And take a look how many edges he had. It has a connection with vertex 2, vertex 6, and vertex 5. It has 3 edges. That is why vertex 1 has 3 degrees, as it has 3 incidents of edges or connection with other vertices. For circuit, let us say here at vertex 1, we move to vertex 6, then goes to vertex 5, and to vertex 4, to vertex 3, and we go back to vertex 6, and we climb up to vertex 2, and back to vertex 1. With this example, we have a path that shows our sequence traveled, and it is closed as we ended up with the starting point. And now let's move on to different types of graphs. There are various types of graphs depending on the number of vertices, number of edges, interconnectivity, and their overall structure. We will discuss some of the important types of graphs that is covered by our lesson in this chapter. And here they are: null graph, trivial, non-directed, directed, connected, disconnected, regular, complete, multi, Hamiltonian, cycle, cyclic, acyclic, finite, infinite, bipartite, planar, simple, pseudo, and Euler. The first type is null graph, one of the simplest type of graph. It is a graph with no edges, but it has vertices. Regardless how many the vertices it has, as long as it has no edges connecting other vertices, it is considered as null graph. Next is trivial graph. A graph that has only one vertex. It has no edges since it cannot be connected to other vertices. Next is non-directed graph. A graph in which all the edges are undirected is called non-directed graph. In edges do not contain any direction on it, but it has a connection with other vertices. We can see in this figure it has connection to other vertices, but it does not hold any direction on where it would be pointing at. In this figure, we can see that this graph consists of 4 vertices and 4 undirected edges. Next is directed graph. A graph in which all the edges are directed. All of the edges of the graph contains direction to other vertices. This kind of graph is also known as digraphs, as it shows the next step or where will be it heading. In this figure, each vertex has its own directed edges that is connected to other vertices. Compared to non-directed graph, its connection doesn't illustrate an arrow. That is one of their differences. Connected graph. A graph in which can visit from one vertex to another vertex is called a connected graph, wherein at least one path exists between every pair of vertices. In this figure, or in this graph, we can see that in the first figure can visit its neighboring vertex to the second figure to connect with one another. Next is disconnected graph, a graph that does not exist any path between at least one pair of vertices. And this graph consists of 2 independent components which are disconnected. It is not possible to visit its neighboring vertex component, as we can see that in vertex D and vertex F, there is no edge, there are no connection with the specific vertex, so they cannot connect the 2 figures. That's why they are disconnected graph. Next is simple graph, a graph having no self-loops and no parallel edges in it. Came from its name, simple. We can see that in this graph, it is very simple as it only shows its vertex and its edges. There are no self-loops and no parallel edges to it. Next is multiple graph or multigraph, a graph having no self-loops but having parallel edges and permitted to have multiple edges. In this graph, we can see that there is no loop or self-loop on it, but it has a parallel connection of vertices A to E. Next is pendant vertex. A vertex with degree 1 is called a pendant vertex. It is also known as leaf vertex. Take a look at this graph. At vertex 6, we can see it has only 1 degree compared to other vertices, as it holds 2 or more edges. If there will be only 1 degree of a vertex, just like in this figure, we can consider that as a pendant vertex or leaf vertex. Next is Euler graph. Any connected graph is called as a Euler graph if and only if all of its vertices are even degrees. Or a Euler graph is connected graph that contains a Euler circuit. In graph theory, a Euler graph is a connected graph that contains all vertices on even degrees. Just like our example here, a Euler path is also known as a Euler trail or a Euler walk. But how we can say that? If a trail exists in the connected graph that contains all the edges of the graph, then the trail is called a Euler trail. And if there exists a walk in the connected graph that visits every edge of the graph exactly once with or without repeating the vertices, then such a walk is called a Euler walk. To check whether any graph is a Euler graph or not, any one of the following may be used. If the graph is connected and contains a Euler circuit, then it is a Euler graph. The other one is if all the vertices of the graph are of even degree, then it is a Euler graph. Next is semi-Euler graph. If a connected graph contains a Euler trail but does not contain a Euler circuit, then such a graph is called a semi-Euler graph. For a graph to be a semi-Euler graph, it must follow two conditions and must be satisfied. First is graph must be connected and graph must contain a Euler trail. Well, in this graph contains a Euler trail. Take a look at BCD, BAD. But it does not contain a Euler circuit. That's why it's a semi-Euler graph. To check whether a graph is a semi-Euler graph or not, make sure that this is connected and contain a Euler trail, and if the graph is connected and contains a Euler trail, then the graph is a semi-Euler graph, otherwise not. And to check whether a graph contains a Euler trail or not, make sure the number of vertices in the graph with odd degrees is not more than 2. If the number of vertices with odd degree are the most 2, then graph contains a Euler trail, otherwise not. A graph will definitely contain a Euler trail if it contains a Euler circuit. A graph may or may not contain a Euler circuit if it contains a Euler trail. A Euler graph is definitely a semi-Euler graph, but a semi-Euler graph may or may not be a. Next is bipartite graph, a special kind of graph, and it has a following properties. It consists of two sets of vertices. We can set them to set x and y. The set of x join only with the vertices of set y. The vertices within the same set do not join. Here is the properties of bipartite graph. Bipartite graphs are two colorable. Bipartite graphs contains no odd cycles. Every subgraph of a bipartite graph is itself bipartite. There does not exist a perfect matching for a bipartite graph with bipartition x and y if x and y is not equal. In any bipartite graph with bipartition x and y, the sum of degrees of vertices of set x is equal to sum of degree of vertices of set y. Next is planar graph. Is a graph that can be drawn in a plane such that none of the edge cross each other. Under it, there's a region of plane or Rn. The planar representation of the graph splits the plane into connected areas called as regions of the plane. This planar graph splits the plane into four regions, region 1, 2, 3, and 4, where in degree 1 or region 1, it has three vertices, that is A, B, and that is D, C, E. In region 2, it has three vertices also, that is B, E, C. And in region 3, it has three vertices also, that is A, B, and E. Region 4 is the whole graph or the whole planar graph itself. Planar graph also has its own properties. In any planar graph, sum of degrees of all the vertices is equal to 2 multiplied by the total number of edges in the graph. The formula below used to find the sum of degrees of all the vertices. In any planar graph, sum of degrees of all the regions is equal to 2 multiplied by the total number of edges in the graph. The formula would be used to have the sum of degrees of all regions. Next is, if G is a connected planar simple graph with E or the edges and V the vertices and R the number of regions in the planar representation of G, then region equals edges minus the vertices plus 2. The next property will be it remains same in all the planar representation of the graph if G is a planar graph with k components, then region equals edges minus vertices plus the quantity of components plus 1. I have here a few examples to exercise some of the properties. Say number 1, let G be a connected planar simple graph with 30 vertices and 60 edges. We are finding for the number of regions of G. Our given are the number of vertices and edges. We have 30 number of vertices and 60 edges. We knew the Euler's formula and it is R equals E minus V plus 2, and we substitute the values and we will ended up with 32. So the regions will be 32 in the graph G. And the next example here, let G be a planar graph with 12 vertices, 3 components, and 9 edges. We are finding for the number of regions in G. And we have our given vertices, that is 12 with 9 edges and 3 components. Solution, we substitute the values and we will end with 1, and that will be the answer. And now let's move on to another kind of graph. Next is weighted graph. A weighted graph is a graph in which each branch is given a numerical weight. It is a special type of labeled graph in which the labels are numbers. As you can see on the figure given below, numerical weight of its edges. Next is Hamiltonian graph. A Hamiltonian graph may be defined as if there exists a closed walk in the connected graph, that visits every vertex of the graph exactly once, except from the starting vertex without repeating the edges, then the graph is called a Hamiltonian graph. Any connected graph that contains a Hamiltonian circuit is called a Hamiltonian graph. This graph contains a closed walk A, B, C, D, E, F, A. That is its path, a closed path. As you can see in this figure, it visits every vertex of the graph exactly once except the starting vertex, as it is a closed path or trail. The edges are not repeated during the walk. In addition, there exists a Hamiltonian circuit in this figure A, B, C, D, E, F, A. And therefore, this is an example of Hamiltonian graph. Next is Hamiltonian path. If there exists a walk in the connected graph that visits every vertex of the graph exactly once without repeating the edges, then such a walk is called a Hamiltonian path. If a path exists in the connected graph that contains all the vertices of the graph, we can consider that also as a Hamiltonian path. In Hamiltonian path, all the edges may or may not be covered, but edges must not repeat, just like the figures shown below. Isomorphic graph. Graph isomorphism is a phenomenon of existing the same graph in more than one form. Graph isomorphism has its own conditions. For any graph to be isomorphic, it must follow four conditions and be satisfied. The number of vertices in both of the graphs must be the same. The number of edges in both graphs must be the same. The degree sequence of both the graphs must be the same. If a cycle of length component is formed by the vertices in one graph, then the cycle of same length component must be formed by the vertices in the other graph as well. Those are the conditions for isomorphism. Next is degree sequence. Is defined as a sequence of the degrees of all the vertices in ascending order. A look at this figure and let us check its necessary condition, as degree sequence holds two conditions for it to satisfy. In the first condition, it must have equal vertices. The number of vertices in graph 1 is 4 and the number of vertices in graph 2 is 4. It satisfies the first condition, while the second condition is for the equal edges. The number of edges in graph 1 is 5. The number of edges in graph 2 is 6. In this condition, graphs 1 and 2 have different number of edges and does not satisfy the condition. Since condition 2 violates, the given graphs cannot be isomorphic. We conclude graph 1 and graph 2 are not isomorphic graphs. Next is equivalent graphs. Two graphs are said to be equal if they have the exact same distinct elements, but sometimes two graphs can appear equal, even if they aren't, and that is the idea behind isomorphism. Isomorphism is a graph can exist in different forms, having the same number of vertices, edges, and also the same edge connectivity. Take a look at the example below. At first, it may seem not equal, but if we take a look at its vertices and edges and connection of vertices, it holds the same connection, the number of vertices, and edges. Next is circuits. It is a path that starts and ends at the same vertex. There are many present circuits in this time, and we are only going to talk about Euler circuits and Hamiltonian circuits. As covered of our topic, Euler circuits, a closed Euler trail is called as a Euler circuit. Euler circuit is also known as a Euler cycle or Euler tour. If circuits exist in the connected graph that contains all the edges of the graph, then that circuit is called as a Euler circuit. If all exits in the connected graph that starts and ends at the same vertex and visits every edge of the graph exactly once with or without repeating the vertices, then such a walk is called a Euler circuit. This is for checking whether a graph contains a Euler circuit or not. Just make sure that all its vertices are of even degree. If all its vertices are of even degree, their graph contains a Euler circuit, otherwise not. A graph will definitely contain a Euler trail if it contains a Euler circuit. A graph may or may not contain a Euler circuit if it contains a Euler trail. Next is Hamiltonian circuit. Hamiltonian circuit is also known as Hamiltonian cycle. If there exists a walk in the connected graph that visits every vertex of the graph exactly once except the starting point without repeating the edges and returns to the same vertex, then such a walk is called a Hamiltonian circuit. If there exists a cycle in the connected graph that contains all the vertices of the graph, then we can call it also as Hamiltonian circuit. A Hamiltonian path which starts and ends at the same vertex is considered also as a Hamiltonian circuit. And here's an important keynotes for Hamiltonian circuit. Any Hamiltonian circuit can be converted to a Hamiltonian path by removing one of its edges. Every graph that contains a Hamiltonian circuit also contains a Hamiltonian path, but vice versa is not true. It may, but not always. There may exist more than one Hamiltonian paths and Hamiltonian circuits in a graph. For our summary, we knew that graph theory is a subfield of mathematics that deals with graphs. Graph theory is the study of the relationship between edges and vertices. The history of graph theory is specifically traced way back year 1735 when Swiss mathematician Leonhard Euler solved the Königsberg Bridge problem. There are many types of graphs like null graph, trivial graph, non-directed graph, directed graph, connected graph, disconnected graph, bipartite graph, planar graph, simple graph, multigraph, Euler graph, and Hamiltonian graph. Loop is an edge that connects a vertex to itself. Path is a sequence of vertices with the property that each vertex in the sequence is adjacent to the vertex next to it. Degree of a vertex is the number of edges incident with that vertex. Circuit is a path that begins and ends at the same vertex. A graph consists of a set of dots called vertices and a set of edges connecting pairs of vertices. An edge is represented by a line or arrow extending from one vertex to another. A vertex or a node of a graph is one of the objects that are connected together. If a graph has more than one edge joining some pair of vertices, then these edges are called multiple edges. And here are the references used in our topic, graphs and circuits. Be ready on our online meeting as I would have a short assessment about this topic. I would be gladly to each and everyone to participate. Thank you for watching my presentation. That would be all. Thank you.